Okay. Hmm. So this class we are going to start chapter 15. It's about oscillations, and one important motion of oscillation is simple harmonic motion. So we are first going to talk about that. S represents simple, H represents harmonic, and M represents motion. So we are going to see what is simple harmonic motion, okay? So we are going to see the definition first. So let's see the definition for simple harmonic motion first, and then we are going to analyze how to describe the motion. So see here, simple harmonic motion is a periodic motion that is a sinusoidal function of time, and the amplitude is not changing, okay? So why we call simple harmonic motion is a very specific oscillation. Remember what is oscillation? Is if you have an object, let me draw an example for you. If you have an object that is going back and forth, this is oscillation. And we have to use a mathematical form to describe the position of the motion as a function of time. So see here, usually we can define this is x equals to 0. And for some specific motion, we can use this equation to represent the motion. And this kind of motion is simple harmonic motion. And a simple harmonic motion, we are going to have a constant angular frequency, and we are going to have a constant speed. So how to find this omega? First, we need to understand what is frequency and what is period. So this object is going back and forth. So think about it's going back and forth, right? The period is the time for one cycle. So it's the time takes the object go from here and then go back to here. Or you can say it's go from here and then go back to here. Okay. So the time it takes for one cycle. So here we have the time in second for one full cycle is what we call period. And what is frequency? Frequency is the number of oscillations per second. So that's why we have the definition period equals to 1 over frequency, which is this guy here. Okay, so now we have period, we have frequency, how to use the motion. So see here, for this motion, if you draw the motion as a function of time, so let's say if you release the object from here, what will happen to the object is it will go to its equilibrium and keep on going back and forth. So if we draw the position as a function of time, we may get a function that looks like this, right? So this is a sinusoidal function, and this guy here is what we call xm. This is the amplitude. And then we also have omega. Omega will be equal to 2 pi times the frequency. So you can kind of see omega is the description of how fast this oscillation is. So 2 pi is usually in radian and divided by second. So 2 pi over period is the, see here, omega equals to 2 pi over period, which is 2 pi times frequency. So it's like angular frequency is the time for like 360 degrees, and this is what we call angular frequency, okay, 2 pi times f. And this is exactly what we have seen, and from xm to our next xm, this is a period. You guys did a lab like a week ago, and we also have a sine and a cosine function, and I ask you to find the two adjacent maximal, and the period is going from here to here. So you know how to get the period. And for the very specific function here, we have some very important parameter goes along with the function. So the function is position as a function of time equals to xm cosine omega t plus phi. So the value xm is how far particle moves in either direction is what we call amplitude. So we have this xm is amplitude. And also we have the argument of cosine is the phase. So what is the phase? The phase is inside the parentheses. So omega t plus phi is the phase. And we also have this little phi here is what we call phase angle or phase constant. So this is actually the angle when we have t equals to 0. So if you have t equals to 0, we will have xt equals to xm cosine phi. So the phi depends on the initial position of the object. So the phase constant phi, it adjusts for initial conditions of the motion at t equals to 0. And we have angular frequency, which is omega. Omega equals to 2 pi times the frequency, or 2 pi divided by the period. So with xm, omega, and phi, we can predict the position of the object as a function of time. So remember, this is a cosine function. Xm is outside, and then cosine omega t plus phi. Okay. So it's a review of this equation. I think you guys know. And this t here is the time. So in the end, we have x as a function of time. Amplitude, angular frequency, the phase, and the phase constant. And we have angular frequency is 2 pi over t, which is 2 pi times the frequency. Okay, so we also talked about that. So now we are going to take a look at this checkpoint here. So a particle undergoing simple harmonic motion of period t and is at negative xm at t equals to 0. Is it at negative xm at positive xm at t equals to 0, between negative xm 0, or between 0 and positive xm when t equals to 2t, 3.5t, and 5.25t. So what does this problem ask you? It actually asks you about what the function look like and what is the position at a given time. So if we are going to draw the picture, initially it's at a negative xm. So we have this negative xm here. We should draw a cosine function that looks like this. Okay. And keep on going. And this is what? This is 1t. Okay. And at 2t, it should be here, right? 2t should be here. So it should be at, so this is 2t. So it should be at negative xm, okay, for 2t. But for 3.5t, because the motion is periodic, after 3t, it go back to the initial position, and then this is 0.5t. Okay, wait, where's 0.5t? I didn't do it right. This is 0.5t. Okay, and what is this? This is 0.25t, okay? So 0.5t, we have the position is at xm. So at 3t plus 0.5t is also at xm. Because after one period, the object will go back to its initial position. So after a period, this guy goes to here. And after a period, so if you have here, after 1t, it go back to the equilibrium. So after a period, it returns to its position. So as long as we can find what happened at 0.5t is the same as what happened at 3.5t. And also here is the same. If we can find out what happened at 0.25t, then it's the same as 5.525t. So at 2.5t, or at 0.25t is here is x equals to 0, so that's why it's x equals to 0. So you can use the picture to understand how to find out the positions, okay? After a period, the position will not change, okay? And the velocity can be found by the time derivative of the position function. So let's go back to take a look at our position function, okay? And we know the first derivative of displacement is velocity. So we can take a derivative of time here, and you are going to get a negative xm omega sine omega t plus phi, right? And first derivative is your velocity. So velocity, I can write it as v. Velocity as a function of time, you are going to get this. The plus 5, okay? And this is exactly what we have here. Negative omega xm sine omega t plus 5. And the omega xm is the amplitude of the velocity, so velocity amplitude. And in the meantime, you can also take another derivative. You can get your acceleration as a function of time, so you are going to get this. The second derivative of position, so take double derivative, sine becomes cosine, and you have this omega here, so omega squared. So this is what you have. And the value omega squared xm is the acceleration amplitude am. And you can see here, this xm cosine omega, there's a t missing, okay, be careful. Cosine omega t plus phi is the same as your xt. So that's why at will be equal to negative omega squared xt. So this is our acceleration for simple harmonic motion. And we have some extreme value. So this is the position as a function of time. You can see maximal value here, minimal value here, 0 here. But if you take the first derivative, you are going to get 0 here, 0 here, and 0 here, and you are going to have minimal value here and the maximal value here. So extreme values here mean object at positive or negative xm here. And in velocity, 0 value here means object at positive or negative xm. So see here. Okay. And here, which is your positive x and negative. And also for acceleration, it's also extreme value object at positive or negative xm. But when you have so maximal or extreme value of velocity happens at x equals to 0. Okay. Oh, Justin is here. Let me give me. Okay. So when we have extreme value for the displacement, then the object, of course, is at the maximal amplitude. But when we have 0 velocity, the object is at its maximal, or is at its maximal displacement. And when we have maximal velocity or minimal velocity, then the object goes through equilibrium. So it's the relation between the derivatives of the cosine function. You only need to remember this. Position as a function of time equals to xm cosine omega t plus phi. Okay, so take derivative, you can get, we should do it here. Take derivative, you can get a velocity. Take a double derivative, you can get acceleration. So these graphs represents the different values, displacement, velocity, and acceleration. And here, in simple harmonic motion, the acceleration A is proportional to the displacement x, but opposite in sign. Okay, so because you take a double derivative, you are going to get a negative omega squared xt. So acceleration is always negative in the negative direction of your displacement. And the two quantities are related by the square of angular frequency omega. So this is what do you know? And then we have another checkpoint. Which of the following relation between a particle's acceleration a and its position x indicate simple harmonic motion? So what we should have a equals to negative omega square x. Okay, why is that? It's from the double derivative. So which one is right? This should have a negative sign so that your omega equals to 2. Where's the negative sign? Okay, maybe this gives you the magnitude. If this is the magnitude, then it's right. Okay, magnitude of acceleration and magnitude. Okay, so the first thing we know is a should be proportional to x. So if you say x squared, and if you say this is not right. Yeah, this should have a negative sign, okay? Otherwise, it's not right. It's a equals to negative omega square x. So we should have, let's erase our magnitude. Let's change our c. This c here should have, I'm going to use my black pen here, so you know it's this. Okay. So a equals to negative omega square x. Okay, be very careful. And then from here, we will have a equals to negative 2 square x, so our omega equals to 2, okay? So this one here is positive. If it's positive, then it's not right, because your omega square cannot be a negative value, okay? So this is that. And we can also apply Newton's second law. So if you have your acceleration, you can calculate the force applied on the object, which is F equals to ma, and your a is negative omega square x. So the force is negative m omega square x. And you can kind of see if it's mass on spring, F will be equal to negative kx, okay? Spring constant. And then your k should be equal to m omega square. This is the same as omega equals to square root of k over m. Okay. So this is the one that we learned in the previous chapter when we talk about Hooke's law. So linear simple harmonic motion mass on spring, we are going to have omega equals to square root of k over m, and t equals to 2 pi times square root of m over k. I don't know if you guys remember this. You did a lab is using the static and also dynamic method to measure spring constant. So you can find the period and use the mass to calculate the k, okay? So this is how to use omega to find your period, okay? So here F equals to MA, which equals to negative M omega square X, okay? So be very careful. This is our force. Okay, so now if we know this, which of the following relations between force F on a particle and the particle's position x gives a simple harmonic motion? A is F equals to negative 5x. So if you take a look at this, your force should be equal to negative something times x. Which one is right? Only this one is right. This one is x squared is not right. This one is x squared is not right. And this one is positive value is not right. So the only thing that is right is the negative value one. Okay, so F equals to -5. X is simple harmonic motion. Okay. And then, so this is the definition for simple harmonic motion. That is very simple. And you remember this equation, which equation? Remember this equation, okay? X as a function of time for simple harmonic motion, and everything else can be derived from this function. First derivative get velocity, second derivative get acceleration, and you can get the relation between x and a, okay? X and your a. So this is the first section. And the second section, we are going to talk about the energy in simple harmonic motion. So for simple harmonic motion, we also have kinetic energy and we have potential energy. So potential energy is kind of like the potential energy stored in a spring. So U will be equal to 1/2 kx squared. And x is, remember what is x? X is also from the previous section. It's xm cosine omega t plus 5, okay? And then what is your velocity? Velocity, you taking derivative, you are going, oh, we can write it this way. Taking derivative of this, you are going to get negative xm omega sine omega t plus 5, okay? Can you write a little bit smaller? Okay, so this is that. And if you want to calculate potential energy, you are going to use 1/2 kx squared. So you are going to square this value, you get this. And if you are going to get your kinetic energy is 1/2 mv squared, and you are going to do m times this guy square, and also m omega square equals to k. So you are going to get this. So why is that? Take a look at this. See, k equals to m omega squared. So once you have your m and you have your omega square here, so you are going to square this whole thing. So you are going to get omega square and x square. So omega square and m equals to k. So you are going to get k square here. And then you are going to get sine square omega t plus 5, okay? So this is how we get that. And then we can do the summation of these two. There is something missing here, sorry. It's k and then xm square. The square is not right here because what you have, I'm going to write it for you, is 1/2 m, and then we have this whole thing square, which is negative square becomes positive. So you are going to times xm square omega square sine square omega t plus 5. Okay, so m omega square is your k, and your xm, you should write it here. So it's 1/2 k xm square sine square omega t plus 5. And then we can add this together because sine square plus cosine square is 1. So we are going to get kt plus ut equals E, which equals 1/2 kxm squared. So the spring constant times xm squared. Okay, so this is the total energy. Yeah, there is something missing here. This square should be xm squared. And you can see how the energy looks like. You have your potential energy looks like this. So see here, you have your potential energy is the green line. You have your kinetic energy is the red line. But when you add these two, you are going to get a straight line. So that's why our total energy is a constant. So as time changes, the energy shifts between the two types, between kinetic energy and potential energy, are the total mechanical energy is constant. So this is the same as one of the lab we did. You remember we have potential energy, kinetic energy, but the total is a constant. So this is the same, but this one here, our kinetic energy looks like this. So this is our KE, and our potential energy looks like this. This is our PE. Oh, actually, we should use U instead of PE. So U and K. Okay. And then we are going to take a look at this example. So in this figure, the block has a kinetic energy of 3 joules, and the spring has potential energy of 2 joules when the block is at 2 centimeter. So the total is what? The total is 5 joules, okay? So what is the kinetic energy when the block is at x equals to 0? So at x equals to 0, because our potential energy equals to 1/2 kx squared, so our potential energy equals to 0 at x equals to 0. And our total E is 5, which equals to U plus K. So that's why if your U is 0, your kinetic energy should be 5 joules, okay? And so that's 8. And your potential energy should be 0. And D, what is the elastic potential energy when the block is at x equals to -2? So at x equals to -2, what is the potential energy? So at x equals to 2 and -2, you are going to have the same potential energy because it depends on the stretchment, 1/2 kx squared. So +2 and -2, when you square it, you are going to get the same value. So that's why it's the same as, so this one here is the same as x equals to +2.0 centimeter. So that's why it should be 2 joules. And at x equals to -xm, x equals to -xm, this is the turning point. So your velocity goes to 0. Then your kinetic energy goes to 0. Everything is potential energy, which is the total energy. Then it's 5 joules. Okay. So be very careful. It's the conversion between the two types of the energy. And then we have an angular simple harmonic simple harmonic oscillator. Okay. So what is angular simple harmonic oscillator? So you guys remember simple pendulum that we did in the lab the other day, this object going back and forth. So instead of x as a function of time, it's a sinusoidal function. Then for this motion, our angle is a sinusoidal function, okay? So that's why we call it an angular simple harmonic oscillator. So we do not describe the position as a function of time. Instead, we have the angle as a function of time, okay? So we have like a pendulum, a torsion pendulum, so moves in angular simple harmonic motion. So instead of position, we are going to use angle, and we are going to replace linear variable, and that's why here we have the torque makes the object go back. Replace linear variable with angular analogs, and then we are going to find, oh, do you guys know what is this? So this simple pendulum is a very, so this pendulum is a very specific example, but if we have a physical pendulum, okay? So we are going to have a torque that try to make the object oscillates to equilibrium, which is somewhere like this here, okay? So we have a torque. Torque usually looks like this. And here we will have torque equals to a constant negative chi times the angle. So the torque depends on our angle here. Okay, because usually our torque equals to F times L times sine phi or sine theta. But for small angle, sine theta and theta will be the same, so you can write it as FL theta. And this FL is our pi here. So basically, this is the torque it's the force try to make the object go to equilibrium, and this is the torque try to make the object go to equilibrium. And the chi here is what we call the torsion constant, okay, torsion constant. So it's the torque makes the object rotating, okay, rotating. So this is more like a rotational angular simple harmonic motion instead of the object oscillating, okay? And then we can have our period equals to 2 pi times square root of I over chi. So remember before 2 pi, k equals to 2 pi times square root of m over k. But we don't have instead we have moment of inertia, and the moment of inertia over the torsion constant, and then it's for angular simple harmonic motion. So angular simple harmonic motion, just use an example like this, okay, something going back and forth, and use angle. Angle is a sine or cosine function. And then we are going to talk about some very simple pendulums and the circular motion. So take a look at this. So a simple pendulum is a bob of mass m suspended from an unstretchable massless spring. And the bob feels a restoring torque. So we are going to have the torque equals to negative FL sine theta. And then relates to the moment of inertia, it's our angular acceleration equals to mgl over I times theta. So what is this? So think about what we have. This Fg here equals to mg, right? And then negative L. And sine theta for small angle equals to theta. And it equals to moment of inertia times angular acceleration. So that's why your angular acceleration will be equal to mgl theta over I. So basically divided by I on both sides. So you are going to get your moment of inertia and angular acceleration. So what is happening is this torque try to make the bob go back to the equilibrium here. So you try to make the bob rotate around this pivot point here. And then we have angular amplitude theta. So what is theta? Theta is this little guy here. And we have our angular frequency, omega equals to square root of mgl over I. And for simple pendulum, I equals to ml. So I remember this moment of inertia. Moment of inertia is summation of mr squared. So for simple pendulum, you have m here, you have l. So ml squared, and put ml squared here. The l get crossed out, and you are going to get the m get crossed out. So you are only going to have G over L here. So this is the period for a simple pendulum. We have seen this equation before in our lab. So we know period only depend on the length of the string, okay? And a physical pendulum is the same. You are going to use omega equals to square root of mgl over I. So what is L? L is this is your L, okay? And what is your I? I is the moment of inertia, okay? And then t period. So omega equals to square root of mgl over I, and then omega will be equal to 2 pi divided by t. So t equals to 2 pi over omega, and then you are going to get this. Okay, period is 2 pi times square root of I over mgh. And you can And a physical pendulum can be used to determine the free fall acceleration g. So we can use simple pendulum to determine the acceleration if you measure the. So we can here see this one is using a uniform rod to determine the free fall acceleration g, because we have this is our I, so you have a rod, this is the moment of inertia, and then our t will be equal to 2 pi, take a look at here, times square root of L over mg h. H, this is the center of mass, so it's L over 2, okay? Okay, this is 1 over 3. Why you have that? Yeah, 1 over 12 plus 12 plus 1 over 4. Yeah, this is 1 over 3. So what we have here is 2 pi times 1 over 3 ml squared over mg times L over 2. Take square root equals to t. So the m get crossed out, and then you have L get crossed out. So you are going to get T will be equal to 2 pi times square root of 2 over 3 L over G, okay? And then you are going to square this on both sides, and then you are going to get your G will be equal to 8 pi square L over 3T squared, okay? And then we can take a look at our checkpoint. It's the simple pendulum. The period does not depend on the mass. So 3 physical pendulums of mass m0, 2m, and 3m0 have the same shape and size and are suspended at the same point. So rank the mass according to the period of the pendulums. Greatest first. So it should be all the same because mass does not affect the period of a pendulum. So you can see your equation. You can see this equation here for simple pendulum. There's no mass in it. Okay. And then we are going to relate our simple harmonic motion to circular motion. Simple harmonic motion is circular motion viewed edge on. What does this mean? We can take a look at the projection of our simple harmonic motion. So let's take a look at the definition here. Simple harmonic motion is the projection of uniform circular motion on a diameter of the circle in which circular motion occurs. So the next figure shows a reference particle move in uniform circular motion, and its angular position at any time is omega t plus phi. So what does this tells you? So if you think, what does this mean? If you have a circular motion like this, I'm going to draw it again. Okay. So if the object is here, then you are going to have a projection on your x-axis, that is this point. And if the object is here going up, then you are going to have a projection here. And keep going up, you are going to have a projection here. And keep going up, you are going to have a projection here, and then projection here. Okay, and then projection here. and then projection here. So basically, it's when the object is doing circular motion, you are going to take a look at so if you have a light here, and you are going to take a look at the shadow of this point on x-axis. What you are going to see here, it starts from here, and then when it keeps going, it goes to here, right? And when it keeps going, then going down, then we are going to see the shadow also go back like this. And if it keep going up, so when it go back to here, it keeps going up, then going up, you are going to have a shadow that looks like this. So if you draw so you have light shining directly at this object, and you are going to get a dot on the x-axis. So the movement of the shadow is the same as a sinusoidal function. It looks like this. So does that make sense? So it's a projection of circular motion on x-axis. So SHM is projection of circular motion on x-axis. Okay, so this is your object, and this is a projection. So the projection will chase out a sine or cosine function. Okay, so that's why we can relate the circular motion to our simple harmonic motion. So if you have the projection, what you are going to do is you are going to add a cosine of the angle, because x. So take a look at this. What is your x? Your projection on x will be equal to xm times cosine theta, right? This is your angle theta. Okay, adjacent side. And our theta depend on omega t plus phi. So that's why we have this. And similarly with velocity and angular acceleration taking derivative. So we find that this projection is simple harmonic motion. So the projection of your circular motion on a fixed axis is actually simple harmonic motion. And then we have something called damped harmonic motion. What is damped? Damped here means in reality, we always have friction and something to prevent the object from oscillation, and then our amplitude will decrease. Then that's damped harmonic motion. So here we can take a look at this. It's when an external force reduce. So here, very important, is reduce the motion of an oscillator, then the motion is damped. So you must have something to prevent the motion and make the motion stop in the end. So that's damped harmonic motion. So think about if you have a pendulum in water, okay? So the water will apply a damping force proportional to the velocity and then slow the object down. And then here, our damping force, so FD, damping force equals to negative BV, and depend on the viscosity of the fluid. Okay, so initially, if you have simple harmonic motion look like this, and then if oscillation exists, you are going to have a decreasing amplitude. So you may have an oscillation look like this. Okay, so this is just a sketch, and then we can solve a second order differential equation, and then we are going to get this. So if you have something in the liquid to prevent the motion, and then we are going to have, what is this? So the force is acting on the object. This is actually net force equals to negative AKX and minus FV will be equal to MA. So this is negative Kx, and this is Fx prime, and this is Mx prime prime. So acceleration is Mx prime prime. So you rewrite these equations, Mx prime prime plus fx prime plus kx equals to 0. So this is a second order differential equation, and the solution to this equation is this. You do not have to worry about how to solve this. Okay, so just remember this is the equation. And then we are going to have our new angular frequency. Instead of the old one, omega equals to square root of k over m. And then you are going to have this new one with the damping constant B in the equation. So that's exactly what we have. The amplitude decreases. And this, you see this purple line here, the dashed purple line, have a function that looks exactly like the coefficient in front of the cosine function, which is xm times e to the power of negative b over 2m. Okay, so it's an exponential decay. Okay, or bt. Is an exponential decay. Okay, depend on the damping constant. And if the damping constant is very small, then our omega equals to omega prime. They are almost the same. And then we have a decreasing amplitude and decreasing energy as a function of time. So take a look at this. Decreasing energy as a function of time, 1/2 kx squared. So you are going to have 1/2 kx m squared e to the power of negative bt. This is 2m. You square it, you are going to have bt over m. Okay, so amplitude. And then we are going to have a checkpoint here. So here are the three sets of values for spring constant k, 2k, k, and 3k. And the mass for the damped harmonic oscillator M0, full M0, and M0. So rank the sets according to the time required for the mechanical energy to decrease to 1/4 of its initial value. Greatest first. How to do that? You take a look at this equation. It's 1/2 kxm Okay, so this is what we have, a kx squared negative bt over m. So initial value t equals to 0, we are going to have this, and then decrease to 1/4 of its value. So you are going to have negative e to the power of negative b over mt will be equal to 1/4. Okay, so 1/4, this guy, to its initial value. X equals to t, this is the initial value, and decrease to 1/4, then this is that. And what we are going to do, we are going to take a look at b over m. So this guy here, b over m is 1, and this guy here, b over m is 6/4, so it's 3/2. And the last one, b over m, is 3. So basically, you are comparing e to the power of negative something t and e to the power of negative 3/2t and e to the power of negative 3t. So which one goes to 1/4 faster? This one is the fastest because you have 3t. This one decays the fastest, so it takes less time. And this guy takes the longest time. So that's why it's 1, 2, 3. So this takes the longest time. Because you have negative 3 here, so this one here decays faster. Okay, so this is the longest, bigger than this, bigger than this. So that's why it's 1 bigger than 2, bigger than 3. So we are going to take a look at e to the power of negative bt. Okay. And then we are going to take a look at the forced harmonic motion and resonance. So this is when we have standing wave. Okay. So forced or driven oscillations are subject to a periodic force. So what does this mean? This means if you have an oscillator, okay, so let's use a pendulum. So every time a periodic force, what does this mean? So periodic force, you can assume there is a force. Every time this object goes to here, you are going to push it. Every time, so it's going back and forth. Every time it goes to here, you push it. So if this happens, this oscillation will not stop because you have an external force, and this is what we call force-driven oscillation. Okay, you have an external force. So a forced oscillator oscillates at the angular frequency of its driving force. So it depends on the frequency of the force applied on the object. And we write it like this, omega d plus phi. So the displacement amplitude is a complicated function of omega and omega zero. So what is omega and omega zero? Omega zero is the natural frequency of the pendulum. So if you think about this pendulum, it has natural frequency omega zero equals to square root of k over m, right? This is the natural frequency. Oh, this is not a k over m. This is square root of g over l. This is pendulum, not a Mason spring. But then we have a driving force have frequency omega d. So this force here also have its own frequency. And then what will happen when resonance happens is these two frequencies, they equal to each other. So the displacement is a complicated function of omega d and omega zero. And the velocity amplitude of the oscillation is the greatest when omega d equals to omega. So the condition is called resonance. So that is your driving force frequency equals to the natural frequency. So this is also approximately when the displacement amplitude is largest. Resonance has important implications for the stability of structure, and forced oscillation at the resonance frequency may result in rupture or collapse. What does this tell you? I want to, although this looks a little bit weird, what is resonance? So every object have a natural frequency. If you have a Mason spring, of course, it's square root omega zero is square root of k over m. And if you have a pendulum, that's omega equals to square root of g over l. But every object, so think about if you have a glass bottle. So this bottle also have a natural frequency, okay? So it can oscillate. If you take a pivot point here, it could oscillate around this point. You take another pivot point here, it could oscillate around this point, but usually we take this guy as our pivot point. But think about, so if you have a pivot point, then you have natural frequency omega zero, right? Using the moment of inertia, you can calculate that. But you guys know sound is a kind of wave because we did it in another day. So if someone here, I'm going to give you an example of resonance, okay? If someone here is singing, so so the sound wave travels to here, okay? So when the sound wave have frequency omega d, when omega d equals to omega zero, what will happen is sometimes you see in the movie is the glass will break or the glass, so here. What will happen is when these two frequencies equals to each other, this glass bottle will start to oscillate and have, so when this have large amplitude oscillation, and then it will result in break. So sometimes in the movie you see a scenario when a singer is singing and then have a high-pitched voice. When the voice matches the natural frequency of a glass bottle, actually the glass bottle breaks. So it's not a magic. It's just when resonance happens, the amplitude of the oscillation will be very large and then it could break. Okay, so this is a resonance. And you also have like other examples when resonance happens. It's if you are crossing a bridge. Okay, if you have a team of football player, or if you have a team of army cross the bridge, if everybody is stepping on the bridge at the same frequency, and when the frequency matches the natural frequency of the bridge, so you can have the bridge oscillate at this point. And then when the frequency of the footstep omega d matches the natural frequency of the bridge, then the bridge will start to oscillate, and then in the end, it may collapse. Okay, so when the amplitude of your oscillation is very large, resonance happens, and you are going to have a very large amplitude. Okay, so this is some natural phenomenon that explains resonance. Actually, we can use resonance to explain some natural phenomena. And also, other things like, I'm going to show you this. Okay. So you also have this experience in your daily life is when you have your pencil here. If you oscillate the pencil at any frequency, this oscillation, the amplitude is not very big, right? Only when you do it at the right frequency, I cannot hold it, but only when you do it at the right frequency, you are going to have a very large amplitude oscillation. So if you do a random frequency, see this. Will anything happen? No. I have a better pencil. So only when you apply the force at the right frequency, you are going to have a large amplitude. Okay, if you do it randomly, then no large amplitude. Right frequency, then large amplitude. And this is also when resonance happens. You have to apply a force here at the right frequency to make the amplitude large. Okay, so I think that will be the end of this chapter. Yeah, that's the end of this chapter. So we have some simple harmonic motion, and we have damped harmonic motion. So the equation to remember is this guy here, okay? And definition for period for frequency, and omega, and energy, and different period, how to calculate that, and damped harmonic motion. And I think that will be, and resonance happens when the driving force, the frequency of the driving force equals to the natural frequency. Usually I use omega 0 as natural frequency. When the two frequencies equal, you are going to have resonance, and you are going to have a very large amplitude. Okay, so this is the end of this chapter, and we have one more chapter to finish. The day after tomorrow, tomorrow is Independence Day, so it's a break. So after Friday's class, we are going to have an exam. I'm going to post the homework solution for chapter 13 to 16 on D2L, so we are not going to have the recitation class. So Friday, we are going to finish chapter 16, and then you are going to have an exam during the weekend. Okay, so I think I'm going to stop here, and bye-bye.